A little while ago, we did an example about an infinite sheet of charge. At least I'm pretty sure we did this example, right? We had, let's say this is the YZ plane. Y cross Z is X, so X is out of the board. And we had this infinite sheet of charge. We'll say this is rho S. The first thing I want to do in this situation is figure out what is the symmetry of the problem? How do I expect this problem to work out? And what I'm observing is that for any location, dq, on this plane, I can choose a dq around it to cancel any vector component except for the x component. Like if I choose a dq here, I can cancel the z component. And if I choose a dq here, I could cancel the y component. I guess for an observation point that is like at 0, 0, but in general, you can choose suitable things to cancel all the vector components except for x. All right, so what I'm going to write down is that I know my electric flux density is going to be some electric flux density magnitude times a hat x, but I don't know what the electric flux density magnitude is. How do I figure out what it is? Consider a side view of this thing. So here's my YZ plane, and x direction is up now. I want to define a Gaussian surface that encloses some of this charge. My Gaussian surface is going to look, it needs to be either parallel or perpendicular to the flux density vector that I know about, so that my dot products are either just d naught times ds or 0. So take a look at this. I know my electric flux density is x directed. It's going to be x directed above the sheet of charge and minus x directed below the sheet of charge, because that is how charges work. The electric flux density points away from them in every direction. The reason that I know that the electric flux density is constant, it has this constant value everywhere. I know that because nothing would change about the problem if I shifted the origin 3 miles to the left or 6 inches to the right. No matter where I put the origin in this picture, I can always do the same symmetry argument, and I always have the same amount of flux density surrounding me because I have this infinite charge sheet. So that's a good way to think about it. Like if you're looking at radial symmetry and you're gonna say something doesn't depend on angle, what happens when you rotate the problem? Does it stay the same? Then obviously it doesn't depend on angle. All right. So here's the thing. We've defined our Gaussian surface. And now we can set up our electric flux integral and our enclosed charge integral, right? So we're going to have our electric flux, making a capital psi, which is going to be the surface integral of d dot ds. The surface normal vector is outward always. So on the top of the box, it points in positive x. The bottom of the box, it points in negative x. And on the sides of the box, it points this way. So that means my electric flux is going to be composed of 4 separate parts. I'm going to have the surface integral on the top of d dot ds, but ds is a hat x times ds, the differential surface element without a vector direction, right? Just the magnitude of it. And this is also x directed. So when I do that dot product, I have d naught a hat x dot a hat x ds. Those just, that dot product evaluates to 1 and I have d naught ds. Seems good. Then I have to add in the sides. Well, this one is an outside. And there's also going to be a top side and a bottom side. Sorry, I guess like a close to me side and an into the board side, because I already called this the top and this the bottom. But there are 4 sides. But on these 4 sides, this is either a hat y minus a hat y, a hat z, or minus a hat z. So in every case, d naught a hat x dot our vector, our surface normal vector, evaluates to 0 because that dot product, those vectors are perpendicular to each other. So we got nothing. And then we have the bottom. Then we have minus d naught a hat x dot minus a hat x. Oops, you can't see that. There we go, minus a hat x ds. Okay. This integral around the sides of the box doesn't do anything. So we only have the contribution of the top of the box and the bottom of the box. And since the top of the box and the bottom of the box have the same physical bounds in x and y, and they have the same arguments once we cancel out these 2 minus signs, we just have one integral that we have to multiply by 2. So our total electric flux is going to be equal to 2 times the integral over the area of the box. Let's say minus a to a and minus b to b of d naught, and ds here is just dy dz. So we end up with 2 times 2a times 2b times d naught. That's the total electric flux out of the box. Now, how do we find the enclosed charge? Look at the same box again. We have a surface charge density here. So although we have to do, although Gauss's law is written for a volume integral, a surface charge density is just a volume charge density with a Dirac delta function in it. So we can write that the enclosed charge is equal to the volume integral of rho v dv, which is equal to the volume integral of delta of x, right? Rho s dv. And then when we evaluate the x portion of that integral, we end up with an integral from minus a to a, from minus b to b of our surface charge density dy dz, excuse me.
Professor, you forgot the minus sign for the second integral.
Oh, I'm sorry. My Can you say that again?
Minus b over b, right? That just is b.
Oh yeah, that should be minus b. Thank you.
Okay.
Okay, so evaluating this integral for the enclosed charge, I end up with 2a, 2b, rho s. Since Gauss's law in its integral form is that the electric flux is equal to the enclosed charge, I can set those two things equal to each other and solve for the magnitude of the electric flux density. And when I do that, the 2a cancels and the 2b cancels. So I have that 2d naught is equal to rho s. So my solution, when I'm writing out my solution here, is that, and I have to provide a vector direction for everything too. So the way to write the solution for this problem is that my vector d is equal to a hat x rho s over 2 for x greater than 0 and minus a hat x rho s over 2 for x less than 0.